So in the last video, I introduced this concept of parameterization. And the basic takeaway for the last video is if you're given two different equations, one telling you the x coordinate, the other telling you the y coordinate, both as a function of time, we can use those two equations in conjunction to come up with a graph, which is kind of cool and definitely different from the standard way of graphing where you just have a single equation that ties together the x and the y coordinate. As I mentioned last time, having two different equations gives you a lot more freedom and kind of adds some cool features to these graphs, like the concept of movement and the concept of speed. From the last video, we learned how do you come up with the graph if you have parameterized equations. We already knew how to come up with the graph if you had the standard form of the equation. In this video, I want to talk about going back and forth between the two. Specifically, suppose you had an equation like we have in red here, and you wanted it to be parameterized. How could I come up with two different equations like we see in purple and blue that represent this curve shown in red? Well, the short answer is there's lots of different ways you can do it. If the equation that you're trying to parameterize is already solved for one of your variables, so solve for the letter y here, for example, then one way to parameterize is just take the other variable, x in this case, and set that equal to t. What I'm saying is my equation for x will be really simple. The x will just be equal to t. And if the x is equal to t, then I can rewrite this equation that I have right here, except instead of writing the letter x, I can write the letter t because x is equal to t. So instead of having y equals 1/2 x plus 2, I would have y equals 1/2 t plus 2. This is a parameterization of this curve. And maybe you can kind of even see how it works, right? If we were trying to graph this equation, one way to do it is to plug in a whole bunch of x values and figure out the corresponding y values. So maybe you'd plug in, 0, 1, and 2 for x and figure out what the corresponding y values would be equal to. Well, think about how we deal with this parameterized set of equations. We could plug in, 0, 1, and 2 for t. If we're plugging in 0, 1, and 2 for t, then x is just equal to 0, 1, and 2, and y is just equal to exactly what it would be over here when we plugged in 0, 1, and 2 for x, because t is really just playing the role of x. Same logic down here. If we wanted to parameterize y equals x squared minus 3, one way to do it is to let x be equal to t, and then y could just be equal to t squared minus 3. Parameterizing a curve that's solved for one of your variables is really easy. Just set the other variable equal to your parameter, t, and substitute in to get the other equation. And you're like, all right, cool, that was super easy. Well, unfortunately, this is just one parameterization. This is the parameterization where time 0 corresponds with x equals 0, and time 1 corresponds with x equals 1, and time 2 is when x equals 2. This is the parameterization where we have this point for t equals 0, and this point for t equals 1, and this point for t equals 2, this point would be t equals -1, and so on, because my x coordinate is just the time. But maybe that's not the parameterization that I want. It's easy to parameterize a curve if you don't care what the parameterization is, if you just want any parameterization. It's a lot harder if we want a specific parameterization. So consider, for example, we want to parameterize something that moves linearly at a constant speed from -2, 1, so from this point right here at time 0, to the point 4, 4, this point right here at time 1. It's moving linearly, so I'll connect these points with a straight line. And when I do that, maybe you recognize this line as the exact same line that we started this video with, y equals 1/2 x plus 2. The line that we parameterized as x equals t and y equals 1/2 t plus 2. However, as we've already seen, this parameterization will not make time 0 over here and time 1 over here, because this parameterization just uses the x coordinate for time, so time 0 would be right here and time 1 would be right here. So how do we change these equations so that this point corresponds with time equals 0? Well, because we have a constant speed and we're moving linearly, this tells us that both x and y as a function of t are going to be linear. In other words, they're going to be of the form m times t plus b. They might have different values of m and different values of b, so maybe I'll call them m1 and b1, m2 and b2 respectively. So the first thing to know is that if you have a constant speed and you're moving linear, that means both of your parameterized equations will end up being linear. I'm not going to prove that fact to you, but you could probably talk yourself into it kind of looking through a few different examples. Where I want to spend our time is figuring out what these equations would have to be. The easiest way to think about it is, because this equation is linear, if we have 2 points on this equation, we can solve for the slope and the y-intercept. But note that the points that I want are not x's and y's, they're x's and t's, the two variables in this equation. I do have 2 points, I have this point and this point. At this point, the x-coordinate is -2, and the t-coordinate is 0. The y-coordinate ends up being 1, but I don't care at all about the y-coordinate of this point because I'm trying to find an equation that relates together the x and the t. At this point over here, the x-coordinate is equal to 4, and the t-coordinate is equal to 1. Again, I'm completely ignoring the y-coordinate because I just want the relationship between x and t. With these 2 points, I can come up with this equation. Since this isn't y equals mx plus b, it's x equals mt plus b, think x is the y and t is the x. So typically when I think about the letter B here, I'm thinking about the y-intercept, but the x is the y. So really it's the x-intercept. It's the value of x when my variable t is equal to 0. That's given right here. Because of this point, b must be equal to -2. This is the thing that's kind of like the y-intercept, but it's the x-intercept because of the variables that I have. If I knew the slope, I'd be done. When you're thinking about the slope, you're probably thinking the change in y divided by the change in x. But again, the x is the y and the t is the x. So instead of thinking about the slope as the change in y divided by the change in x, think about it as the change in x divided by the change in t. If I call this x1 and t1, x2 and t2, I can calculate the slope by taking this 4 and subtracting this -2, and then dividing it by this 1 minus this 0. 4 minus -2 is 6. 6 divided by 1 is equal to 6. The slope of this line is 6. The equation of the x-coordinate is m times t plus b. It's 6 times t minus 2. Not sure you followed that? That's okay. We get to do it again when we come up with the equation for the y-coordinate. We want y in terms of t. You're probably much more comfortable with y in terms of x. So think that the y is playing the role of the y, but the t is playing the role of the x. I need 2 different points relating together the y-coordinate and the t-coordinate. So when t is equal to 0, the y-coordinate is equal to 1. And when t is equal to 1, the y-coordinate is equal to 4. The y-intercept is the value of y when my variable, t in this case, is equal to 0. That's this point right here. This tells me that the y-intercept, the letter b, is equal to 1. For the slope, you're probably thinking the change in y divided by the change in x, but in this case, it's the change in y divided by the change in t. So it's 4 minus 1 divided by 1 minus 0. It's 3. Y as a function of t is equal to 3t plus 1. Not sure if we did all this right? Well, it's easy enough to check your answer, right? If we were starting out with these parameterized equations right here, where x is equal to 6t minus 2 and y is equal to 3t plus 1, and we wanted to come up with the graph, what we could do is keep track of some t values in the corresponding x's and y's. Maybe we could look at when t is equal to 0 and t is equal to 1. When t is equal to 0, if I change all my t's into zeros, I get 6 times 0, or 0 minus 2, so I get -2. When t is equal to 0 down here, I get 3 times 0, or 0 plus 1, so I get a +1. What about when t is equal to 1? 6 times 1 is 6, minus 2 leaves me with 4. 3 times 1 is 3, plus 1 more leaves me with 4. At time 0, I should be at the point -2, 1, which is exactly where this point is. At time 1, I should be at the point 4, 4, which is where this point is. If I was interested in where this particle would be at time 2, all I'd have to do is plug 2 into these equations. 6 times 2 is 12, 12 minus 2 is 10. 3 times 2 is 6, 6 plus 1 more is 7. At time 2, my x-coordinate would be 10 and my y-coordinate would be 7. Doesn't quite fit on the graph, but somewhere up here. Oh yeah, that makes sense. This thing is moving at a constant speed, so I'd move the same distance between time 0 and time 1 as I would between time 1 and time 2. The big takeaway here is if you have the equation of a curve in its standard form, like y equals 1/2 x plus 2 or y equals x squared minus 3, and you just want any old parameterization, it's really easy. Just pick the variable that's not already solved for and let that be equal to t. That's probably the simplest parameterization, but that's just one parameterization. There's infinitely many that represent the same curve, because there's infinitely many ways we could have this particle travel and still be on this line. It could start right here and move really slow. It could start out here and move at a medium speed kind of backwards. It can start here and move pretty quickly in this direction. If we don't care what parameterization we get, it's super easy. If we do care what parameterization we get, then it's pretty challenging. In fact, it quickly gets too challenging for our class. In our class, the only time the parameterization will be specified will be when we're moving linearly at a constant speed, and you'll just know that what that means is both the x-coordinate and the y-coordinate as a function of time is a linear equation. So as long as we have two different points, we can solve for those equations the same way we'd solve for the equation of a line if we had 2 points on that line. In this video, we learned how to go from standard form to the parameterized form. In the next video, what we're going to do is learn how to go from the parameterized form back to the standard form. I probably could squeeze that into this video, but I kind of want to keep them short, so I'm going to stop this one here.